Hey guys, Miss Marusik here, and in this video we're going to talk about mechanisms and how I can use a mechanism to determine the orders of a particular rate law expression of a reaction. Now, we talked about in a previous video how in order to have a successful collision where reactants will turn into products, I have to collide with enough energy and in the correct orientation. And unfortunately, when I have three or more molecules, it's really hard to get them to collide all at one time with the sufficient energy and in the correct orientation. So it's much easier to collide them in steps. One molecule bumps into another one, then that bumps into another one, and so on and so forth. And so that order of steps of those collisions would be referred to as a mechanism. So it says here that a reaction mechanism suggests a series of elementary reaction steps by which collisions actually occur. So it shows the order of which we're breaking bonds and then forming the new ones, the order of those collisions occurring. Now, a reaction mechanism is technically theoretical. We're not for certain with a mechanism whether or not that is the exact order by which things occur, but we can use experimental data to back up if a mechanism is possible. So while we might not be sure that that's for sure the correct mechanism, we can at least say if a mechanism is possible. And so we'll practice with doing that here in a little bit. Now, what we're going to look at below this is an example of a reaction that uses a mechanism in its process, that it's not just a simple reaction. And what we see first here is what is called a potential energy diagram, sometimes referred to as an energy profile for a reaction. We actually saw these in a previous video as well as back in pre-AP, but most of the time when we've seen these graphs before, they just have one hop that occurs between reactants and products. And you notice this has several hops that are occurring. It's not just as simple as reactant going to product. We have reactant going to these substances, then changing to these, and then finally changing to our products. So what that means is that when we see those multiple hops in these energy profiles, we are dealing with some sort of mechanism that occurs in multiple steps. And the number of hops that we see indicates how many steps to the mechanism there are. For example, this has a grand total of 3 hops in it, and so therefore I can predict that this mechanism would have 3 steps to it, or 3 elementary reactions to it. So the first thing it asks us to do is to write an overall balanced reaction for the process. To do that, I don't really care what's happening in the middle. I care about what I have at the beginning and what I have at the end. I see I started with H2 and I2, and I ended with 2HI, and so that's my balanced reaction. They also next ask if the overall reaction is endothermic or exothermic. And so what I would do is look at the potential energy of my reactants, the potential energy of the products, and see if I went up or down over time. I can see that the graph decreased as I went from reactants to products. And so if it decreased as I made that change, then what that means is that change in potential energy was released as heat. And so therefore this would have been an exothermic process. By the way, if the reactants had been lower than the products, so the products had been higher up here, then that would have been endothermic. So next, it asks us to address what are the elementary steps for each of these reactions. So I notice in the first step, I went from H2 to I2, and it changed into H2 and 2I. So that's what I wrote here. The next step started with this H2 and 2I, and then changed over into H2I and I. And so that's what I wrote here for step 2. The third step went from this H2I and I into the 2HI, into my final product. And so that's what I wrote here. And so each of those steps are my elementary reactions that these 3 steps combined together tell me what my mechanism is for this process. So these steps are what are referred to as the mechanism. Now, I want you to kind of pick out a couple things. First off, some of these substances look kind of weird. Like I see here iodine by itself, and that looks kind of odd. Like we know that that's a diatomic. But remember, when I'm dealing with these in-between steps here, I'm not dealing with final substances. And so therefore, I might see some unusual formats to things where I wouldn't have that format at the beginning or at the end. So that iodine is a great example. Even that H2I, like that looks kind of weird. We know charges aren't balanced there or anything. But again, these are just temporary steps until we get to that final product. So things might not always look normal there. Now it mentions on here something called an intermediate. And it says that intermediates are substances that are formed in earlier steps and consumed in later steps, so they are not shown in the overall reaction. So what I did to pick out my intermediates is I asked myself, hey, what substances do I see in this mechanism that I don't see in this overall balanced reaction? And I noticed this H2I and these iodines that are singular. And so if I notice, they are made in one step and then used up in later steps. And so in that process, what's happening is that we would consider these substances as intermediates. They are temporary structures until I get to those final structures. Now, the last question actually asks us something that we talked about in a previous video. It asks, which of the three individual elementary steps would you predict to occur the slowest? And it gives us a hint here of looking at the activation energy of each step. So if you notice back up here, I used some blue arrows to show the activation energy of each step. So from the reactants to the top of this first step, this blue line would be that first step's activation energy. From the intermediate to the top of the second step, that would be its activation energy. And then for our third step, it would be from this intermediate up to that activated complex of that third step there. So if I'm looking at these, I notice that this third step has the largest activation energy. And if you remember from a previous video, we said that the larger the activation energy is, that indicates that that is a slower reaction. So of these three steps, step 3 must have been the slowest. And the reason why is because that activation energy is so high, not enough molecules have enough energy to make it over. And so that slows down the process. It takes a lot longer time to run over a mountain than it does a little hill. And so not as many molecules can make it over that mountain to the product. All right, let's go ahead and switch to the next page. The next page talks about using mechanisms to determine our rate loss, to determine our orders. So as a throwback to our previous video, we looked at the fact that a reaction rate can be expressed as a K, a constant, with our two reactants raised to a particular order. And so what we're going to do is we're going to look at how I can use these mechanisms to determine the orders for an overall reaction here. Now it says that each elementary step reaction in a mechanism has a rate law expression associated with it. Now, as long as we are trying to write a rate law expression for an elementary step, not for the overall, but for an elementary step, the orders will equal the coefficient, which means that all I would have to do is to determine the orders of a particular reactant, to determine that X and Y, I would just look at the coefficients of that substance. That only works if I'm doing the elementary steps of a mechanism. So here's the deal. I have a mechanism right here with 3 elementary steps, and eventually we're going to try and figure out what the overall reaction is. But what I want to start by doing is writing a rate expression for each of these elementary steps. So as a reminder, rate is always equal to some rate law constant, Now on here they used A and B because that was representative of the reactants. Here my reactants are A and G, so I'm going to use those instead of using A and B. So my first reactant is A. Now I see A has been written twice, but writing it twice is the same thing as having a 2 for a coefficient. So that means A is raised to an order of 2. G, on the other hand, has no coefficient with it, so that's an understood coefficient of 1. And so therefore, it's going to have an order of 1. You can either leave it blank or you can write a 1 there. Either would be acceptable. Leaving that 1 off would still be considered an order of 1. All right, we're going to do the same thing for the next 2 elementary steps. So again, rate equals some constant. These constants, by the way, would be different for these 2 reactions because they are different processes. Okay. My first reactant is C. It only would have a coefficient of 1, and so therefore it would have an order of 1. You can either write the 1 or leave it blank. And then I also have a reactant of B. So again, we're only doing this for the reactant side. I'm going to do the same thing for the third step here. So here I have D and B. They both have a coefficient of 1. And so therefore I'll have K with D in brackets and B in brackets, remembering brackets indicate molarity. So there's my 3 individual rate laws for each elementary step. Now here's the deal. If I want to figure out an overall rate expression, I've got to have a little bit more information. So we'll talk about that here in just a moment. It does also ask us to address what the overall chemical equation for this reaction will be. And so what I need to do is I kind of need to pick out things that stayed the same from side to side on these processes. So I'm going to actually kind of almost split up here down the airs. So think of the airs as being an equal line. And I want to see if there's anything that stayed the same from this side of these equations to this side of the equations. And again, I'm looking overall here. So if I see it in one step on the reactant and one step on a product on another one, then I can cancel it out. So I notice here G is present in reactant and product on 2 different steps. C is present in product and reactant on 2 different steps. And D is present in product and reactant on 2 different steps. So being present on one side and then the other allows us to cancel those out. Now, some of you are saying to yourself, well, hey, I see B in 2 different reactions here. But notice both of those B's are on the reactant side. One wasn't on the reactant and the other on the product. So I can't cancel those out. So now when I come down here to write my overall chemical equation for this process, what I'm going to do is I'm going to write everything that did not cancel out from side to side. So I had 2 A's, and instead of writing those separate, I'm just going to write a coefficient of 2 with it. I also had 2 B's on this reactant side. On the product side, if I kind of look, I had an E. And I also had 2 F's. So this would be my overall reaction. And I can see here, or the reason why I would have probably had a mechanism here, I had 4 molecules that all needed to collide. And so again, getting those to all collide in the correct energy and the correct orientation would be very difficult to do all at once. So it makes sense that these would be done in elementary steps. So now here's the deal. How do I get the rate law expression for this overall chemical equation? We said up here that this using the coefficients does not work for the overall. I have to have a little bit more information in order to be able to do this. So it mentions here that the overall rate of a complex reaction, such as our overall here, depends on the slowest step of the mechanism. Only the slowest elementary step is used to write the rate law expression. So what that means is that whichever of these three steps is the slowest would determine what my rate law expression for this overall process would be. Now you're thinking, well, why does the slowest make a difference? Well, it gives an analogy on here about cars on a one-way road. I'm actually going to give you another example. If you've ever seen the movie Monsters University, where Mike and Sully are at college, there's a point where they're having to run a race with their team. It's them and several other team members, and they have to run through this tunnel with these poisonous little animals in it. And what happens is that Mike and Sully just bust on through and they pass by all the other groups and they're like, woohoo, we won, right? Except they didn't win because in order to win, their entire team needed to cross the finish line. And so unfortunately, they were in last place because their slowest members didn't cross the line until last. So you're only as fast as the slowest member on the team. Same thing goes here. You're only as fast as your slowest elementary step, the slowest member of the team. And so let's say they had given us some more information here. Let's say they had told us that maybe this elementary step number 1, that this was a fast step, and that elementary step number 2 was a fast step. But then elementary step number 3 was a slow step. What that would mean is that this slow step would be called the rate determining step. And so it would tell us the rate law expression for this overall. So if this was the slow step, then this would have been the rate law expression for our overall reaction. And you can see this may or may not match up with the coefficients here. It depends on that mechanism. So this overall rate law expression may or may not match up coefficient-wise to your overall chemical equation. Why? Because that overall rate is determined by the slowest step. Now, there's some other things that we can identify in these processes. We can identify what are called intermediates. We already saw a little preview to that, as well as what are called catalysts. An intermediate is a temporary substance that is both made then used somewhere in the mechanism. And they almost never show up in the final rate law. They can every once in a while. It just kind of depends, but usually in BP, they do not show up, okay? A catalyst is another substance we're familiar with, and that is a substance that is used, then reformed, okay? So if I want to pick these out, what I would do is I would come back up here and look for substances that were not present in our overall chemical equation, but that we saw up here. And conveniently, those are things that we probably circled. So for example, let's look at G. I see that G was put in at the beginning and then reproduced at the end. It was used, then reformed. So I had it at the beginning and I had it at the end. It was unchanged, but it helped this reaction to take place. Now think about something that we talked about in a previous video that I put in. I have it at the beginning and I have it again at the end, but overall it remains unchanged. That means G was a catalyst here. Okay, let's talk about C. C was made here, then it was used up again. So what that means is that I made it temporarily, but then I used it right back up. It wasn't present at the beginning, it wasn't present at the end. I just made it, then used it somewhere in the middle. So what that means is that C would be considered an intermediate. Okay, we had one more substance that was not in this overall equation. That was D. So take a second. Do you predict D is an intermediate or a catalyst? Which one do you think? Well, let's see. D was made and then used back up. So that means it wasn't present at the beginning. It's not present at the end. And so therefore, D would also be an intermediate here. By the way, one quick thing I want to mention, and you see an energy profile here. A lot of times what you'll notice is that on a catalyzed reaction, even though we've lowered the activation energy, a lot of times a catalyst enables us to perform the reaction in steps, that by doing it in steps, that's how the overall activation energy is lowered. So you notice for this one, while the uncatalyzed reaction has a really big activation energy, the catalyzed reaction ends up doing it in 2 steps, but that lowered the activation energy overall. So I never had to gain as much energy as I would have for that singular collision. That doing multiple collisions was a little bit easier. Now, what we're going to do next is we're going to ask ourselves if a reaction mechanism is plausible. Remember, we can't know for sure if a reaction mechanism is exactly the way it happens, but we can at least say if it's possible or not. So the first thing we want to make sure that happens is that the elementary steps add up to match the overall reaction. We want to make sure when I add up these elementary steps that this overall chemical equation is the same as whatever they tell me the overall chemical equation really is. Next, we would want to write a rate law expression for our slow or rate determining step and see if that matches up with what they experimentally figured out was the rate law. Maybe they ran a differential rate law experiment or an integrated rate law experiment, and so they mathematically figured out the orders. And so we want to see if our mechanism matches the orders that they got from doing some sort of experiment. So let's go ahead and flip the page. All right, so here we're given an example where they have given us an overall balanced reaction, and they said, hey, we ran this in lab, and experimentally we figured out that the rate law expression was K NO2 raised to an understood order of 1, since there's no exponent there, and F2 also raised to an order of 1. And it wants us to determine which of the following mechanisms is most plausible for that process. So again, there's 2 things we want to check. First, we want to make sure that the overall reaction for these mechanisms matches the overall reaction we see here. Next, we would want to check that the slow step, the rate determining step, has a rate law expression that matches this experimentally determined one. Again, they must have done some sort of experiments in lab, either using differential or integrated data, and figured out what these orders would be. And so let's start off with our first one here. They give us just the same reaction we see here. So they're indicating that we're going to check to see if maybe these all collided at once together, that there was no mechanism. So obviously we know that the overall reaction matches here. That's not going to be a problem. So what we want to do next is we want to see if the rate law matches. Now, if I assume that this is the only elementary step, I would say that rate would equal some constant, my first reactant of NO2 raised to its coefficient of 2, and my second reactant, F2, raised to its coefficient of 1, which again, I don't have to write the 1, so I'm just going to leave that blank. And I'm going to ask myself, does this match up with the experimentally determined rate law? And I'm like, well, this has an order of 2, but that NO2 here only has an order of 1. And so what that means is that this does not match. And so therefore I know that this is not possible, that this did not all collide at once. So what that means is that one of these other mechanisms must be how this collided in order. So let's check the next one. Again, first what I would want to do is make sure my overall reaction matches the overall reaction here. And so I'm going to look from side to side to see if there's anything that would cancel out. I notice FG and FG here are the same from side to side, so those would cancel out. And so that leaves me with 2 NO2 and the F2 going to making 2 NO2F. And I see, hey, that matches up with my overall equation here. So I know that the reaction is okay. So the next thing I would want to do is write my rate law for this mechanism. Remember, the slow step is the rate determining step. You want to commit that to memory. The slow step is the rate determining step. Here is my slow step. The rate law formula for this would be K. I have NO2 raised to an order of 1, and F, just F, raised to an order of 1. And I'm like, well, wait a minute. This has just F in it. This has F2. That does not match. And so therefore, again, this is not a possibility. Let's check our last one here. Again, I'm going to look for things that stay the same from side to side. And I'm like, oh, well, hey, F and F stay the same from side to side. And I'm like, oh, this looks pretty similar to what I saw here. The NO2, NO2, and then the F2, and then the 2 NO2F. So that's all the same. But they flipped around who the slow and the fast is. So I know this overall reaction is going to match up because it's the same for both mechanism 2 and mechanism 3. But on this one, I'm going to write my rate law for my slow step. So again, rate equals sum K, the NO2 raised to an exponent of 1 because the coefficient is 1, and then F2 raised to a coefficient of 1, an exponent of 1. And I'm like, oh, wait a minute, look at that. It matches my experimentally determined rate expression. So since this one does match, this would be my plausible mechanism. I'm not 100% sure that's how it happens, but this mechanism at least matches the data that I was given. And so again, if you wanted to justify why it was plausible, you could mention that the overall reaction of the mechanism matches the given overall reaction, and that the slow rate determining steps rate law expression matches the experimentally determined one. Those are the two things that you could mention to justify why that is an appropriate mechanism. All right, let's look at the next example. It says, hey, the suggested mechanism for the reaction between hydrogen peroxide and iodide ion is shown below. And what it wants us to do is to first address what is the overall reaction for the process. So again, I'm going to look for anything that stayed exactly the same from side to side. I noticed that IO negative stayed the same from side to side. I also noticed that I negative, iodide ion, stayed the same from side to side. And so what I'm going to do here is write everything else that I had here. I had 2 of the H2O2s. And I'm going to go ahead and put that state of aqueous. And that gave us 2 of these H2Os. And O2. So next it asks, what would be the rate law expression for the process? So again, rate laws are determined by the slow step. The slow step is the rate determining step. And so when I look at that slow step here, I'm going to go write that rate equals some K that I don't know yet. My first reactant in that was H2O2. My second reactant in that was iodine to the negative first. Both of those are raised to an order of 1 because they both had coefficients of 1. All right, the next question wants us to identify any intermediates and or catalysts in the process. So let's look at the things that we marked out that aren't in this overall equation here. We had iodine. Let's look at it. Iodine was put in at the beginning and then returned at the end. So if I have it both at the beginning and at the end, and overall it remains unchanged, then that means that iodine here was a catalyst. All right, let's look at the IO negative. The IO negative was made, but then used right back up. So it was not present at the beginning and not present at the end. It was made and then reused. So if it's made and used, then IO negative 1 would be an intermediate. So again, if you had to justify why something was a catalyst and an intermediate, what you could say for a catalyst is that it gets used, then reformed. Or you could say you have it both at the beginning and the end, and overall it remains unchanged. And for the intermediate, it gets made, then used. So you see it kind of does it in the opposite order there. So that's a great way of justifying which one is which. Now, I do want to point out that in this rate law expression, we did have a catalyst remaining in there. That can happen. It's not common to see, but it does take place. Also notice that the coefficients in here didn't match the overall reaction at all. Your rate law expression is always going to match the rate determining slow step. So just because you have certain coefficients happening in that overall reaction does not mean you're going to see those in your rate law expression. All right, it asks one more question on here. It says, hey, if the overall reaction is exothermic in nature, sketch a possible energy profile for this reaction. So first I'm going to put my axes in. On a potential energy diagram, you would have potential energy over here. And I'm just going to put PE for potential energy. And then down here, you would have the progress of the reaction. Okay. So now, as far as the curve is concerned, I know it's exothermic in nature. So that means I'm going to start high and end low. I don't know where those are, so I didn't put any numbers on here, but I at least know that I'm going to start high and low. I also know, based on the fact that I have 2 steps here in my mechanism, that when I draw this, I'm going to have 2 hops. However, let's think about which hop would be bigger, which one would have a greater activation energy. Remember, our slow step, the reason why it's slow is because it has a high activation energy. The fast step would have a lower activation energy. So what I'm going to do is I'm going to draw 2 steps down here where the first one has a really big activation energy and the second one only has a little one. And I don't know where this intermediate would be. I don't know exactly how high these activated complexes are going to be. I just know that the first hop is going to be big and the second hop is going to be a lot smaller. And I also know that it's going to have 2 hops because it had 2 steps to the mechanism. And I know that it's going to start high and end low because it was exothermic in nature. All right, on the last page, you have an example there. And what I want you to do is go ahead and pause the video and take a moment and see if you can solve it. So go ahead, pause that video, try it out. Okay, I'm going to go ahead and put my answers up there so you can see how you did. For your overall reaction, you should have had NO2 plus CO yields NO and CO2. Notice that there was an NO2 that canceled out from side to side, and NO3 canceled out from side to side. So the rate law expression is determined by the slow step, and I noticed NO2 happening twice, so you could either write those separate like so, or because there's two of them, so really it would have a coefficient of 2, I could have put rate equals K NO2 raised to an order of 2. I could have combined all that together. This one had an intermediate of NO3, and it actually had no catalyst. So keep in mind, you don't always have to have both an intermediate and a catalyst. It depends on the mechanism that you're given. Now, this is where I always get the question, well, what about this NO2 here? Why didn't I put that as an intermediate or a catalyst? Well, it's because NO2, even though one of it canceled out, it was still in this overall reaction. It was still present there. So it can't be an intermediate or a catalyst if it's in that overall equation, even though it might be canceling out from side to side. So just be careful with that. All right, this last part of the problem here is kind of a throwback to our last video. It said, hey, based on the rate law expression, what would happen to the rate of the reaction if the concentration of NO2 was doubled? Well, if NO2 gets doubled, that's raised to an order of 2, and so 2 squared would make us 4 times faster. So doubling that concentration would quadruple your rate. Now, this last one's kind of interesting. It says, hey, what would happen to the rate of the reaction if the concentration of CO is doubled? Carbon monoxide was one of our original reactants here. It was in that overall process. But if I look at this rate law expression, I notice that it's not there. And so if it's not there, then that means doubling it would do nothing. What that means is that the carbon monoxide must have been 0 order, which is why it was not shown in the overall rate law expression. All right, hopefully you're feeling really good about addressing these mechanisms. Hopefully we feel confident with identifying our slow rate determining step and using that to write the orders of our overall reaction. If you have any questions or need any help, please feel free to email me. Bye, guys.